Hi everyone, this is Anand and today we will be discussing the problems and solution of CodeDrift. Hi everyone, so today in this video I will be discussing the problem Rpf algorithm. So let us first read the problem. So the problem says that Richard was successful in developing the algorithm and now he has an established company Pied Piper with their unique logo. They have received funding from Peter Gregory to Gavin Belson, the CEO of Hooli, cannot back down from this race, so he ordered his team to reverse engineer Richard's algorithm. Hooli's team is having a tough time breaking it down. Today they are stuck at a randomization state. So there is a sub part of the compression algorithm called RPF algorithm. Okay, so the name of the problem is also RPF algorithm. So what this algorithm says that in this algorithm, when you input an integer x, it returns a random prime factor of this number. Okay, and then you divide this number with the output prime number and obtain a new number. You repeat this process until x is compressed to 1. Okay, let us define the path of a number a. The path of a number x is defined as the different numbers that a changes to before it reaches 1. For example, if x is equal to 12, the different possible paths are 12 to 6 to 3 to 1, or like 12 to 6 to 2 to 1, and or 12 to 4 to 2 to 1. Okay, so Hooli engineers came across this huge number x, which is represented as a product of an integer array a of size n. They were stuck finding the number of paths that the number can take using this algorithm. Okay, since the engineers cannot handle big numbers, we need to find the answer modulo 10 to the power 9 plus 7. Okay, so what it the question says is that basically, like, given a number x, okay, given a number x, okay, what we can do, we can just take any prime factor of this number x. Let's say we take some prime factor of x which is equal to p, and we divide x by p. Okay, so the new value of x become equal to x by p. Okay, we again try to find some another prime factor of this new number x by p. Let's call it q. We divide x by p with that number. Okay, so that become x by p into q. Okay, so we keep on doing this until we reach 1. Okay, so we need to find that how many these sequences are possible. Okay, so how many sequences of prime numbers you can keep on take, how many sequences of these values like x, then x by p, then certainly x divided by p into q, like this you can take. For example, in the case where x is equal to 12, if you see, let's say x is equal to 12, so from 12 you choose one of its prime factor, which is, let's say, 2. You divide 12 by 2, so you get 6. Again choose any random prime factor of it, let's say 3. So 6 by 3, it becomes 2. It has only one prime factor 2, so it got to 1. Similarly, from 12 you can choose a prime factor, let's say 3. Then 12 changes to 12 by 3, 4. 4 has only one prime factor 2, so you divide 4 by 2 and you divide 2 by 2, so it got to 1. And similarly you can also divide 12 by 2, so it got to 6. From 6 you choose a prime factor 2, so 6 got converted to 6 by 2, which is 3. 3 has only one prime factor, so 3 by 3 is 1. Okay, so in this way you can see that for x is equal to 12, there are like 3 possible paths which we can take. So our answer in this case will be equal to 3. And so what we are given is not a single number x. Basically we are given an array of numbers, basically n numbers like this, a1 a2 up to a of n. So our x is basically equal to a1 into a2 up to a of n. And what we need to do, we need to find the number of possible paths, number of different paths modulo 10 to the power 9 plus 7. Since this number can be huge, this number can be very huge to handle it in integers, so that's why we need to print its modulo 10 to the power 9 plus 7. So for example, if the array looks like 2 3 2, then our x will be equal to 2 into 3 into 2, which will be equal to 12. So, and as we found earlier also that for x is equal to 12, we had 3 paths. So our answer in that case, will be equal to 3. Okay, so we will return answer to be equal to 3. Okay, so before heading towards the approach, let's see that if you analyze the previous example for the case 12, so if you just transform 12 like this, at 12 to 6, then 6 to 3, and then 3 to 1, so what we can notice that while transforming 12 to 6, we choose the prime factor to be 2. While transforming 6 to 3, we again choose the prime factor to be equal to 2, and here we choose the prime factor to be equal to 3. Similarly, if you transform your 12 to, then let's say 4, then 2, then 1, then here we choose our prime factors like this. First we choose 3, then we choose 2, and then we choose 2. Now if you have transformed your prime factors like this, that you are choosing your 12, then let's say 6, and then 2 and then 1. Then here the prime factors which we are choosing is like, first we are choosing 2, then we are choosing 3, and then we are choosing 2. So one thing you can notice is that if you see the pattern, like here the prime factors are being chosen in this order, 2, 2 and 3. Here it is chosen in this order, and here it is chosen in this order. So what you notice is that if you just multiply all these numbers together, you will basically be getting 12. Okay, and like these things are nothing but the permutations of the prime factorization of 12. So if you simply prime factorize 12, you will be getting 2 square into 3, which means 2, 2 and 3. Okay, so all these numbers like 2, 2, 3, 3, 2, 2 and 2, 3, 2 are basically the permutations of this list of prime factors of 12. Okay, like with the same occurrence of every prime factor. Like if 2 has occurred here 2 times, then in each transformation sequence, like this one or like this one or like this one, 2 will also be occurring 2 times. Similarly, 3 has occurred 1 time, so in all of these 3 transformation sequence, 3 is occurring for 1 times. Okay, so this is the observation also, that that the observation is that the different number of paths of transformation, or you can say, okay, yeah, transformation is equal to the number of permutations of the list of prime factors, Okay, so if a prime number, so if there is a number x, and if you represent it like this, like let's say p1 to the power x1, then p2 to the power x2, and let's say x has k prime factors with pk, and pk occurring for xk times, then in how many ways can you simply permute all these factors? So basically that will be given by so what it means, let's see first. It means that p1 is occurring for x1 times, then this p2 will be occurring for x2 times. Similarly, pk will be occurring for xk times. So the number of ways of permuting them, permuting them will be equal to like x1 plus x2 up to xk factorial divided by x1 factorial into x2 factorial, so on and so up to xk factorial. Okay, so in this way we can just find the number of paths, okay, by calculating the number of permutations, okay, using this formula. Okay, now since we are not given the actual value of x, we are given x as some kind of array like this, a1, a2, so on and so up to n. So what we will do, we can just simply add the frequency of the prime factors over all the numbers. Okay, so let's say if there is some prime number p which occurs for, let's say, x1 times in a1, and p occurs for x2 times in a2, so on and so up to. So what we will do, so the occurrence of p will be equal to x1 plus x2, like we simply add all the occurrences of p over all the numbers. Okay, so for doing this you can use a map or something like that, and once you store the frequency of all the prime numbers, so what we do, we just store the total frequency of prime numbers over all the array elements. Okay, since x is equal to a1 into a2, so on and so up to a of n. Okay, so if a1 contains like p1 to the power x1, then if a2 contains p2 to the power x2, so on and so up to if it contains pn to the power xn, not p1, like if I assume like for a certain power of p. Okay, so if there is certain power of p, okay, so p occurs, let's, for x1 times in a1, then if p occurs x2 times in a2 and p occurs for xn times in an, then obviously in the product p will occur for x1 plus x2 plus xn. Okay, so that why for every prime number p, we will be storing the total frequency, okay, of all the prime numbers over all the array elements. We will just sum up them together. Okay, now once we did this, once we know all the prime numbers and their respective frequency in the number x, we can simply calculate the number of paths as like the total frequency, like the sum of total frequency of all prime numbers, okay, that's factorial, divided by the frequency of every prime numbers factorial, every prime number factorial. Okay, so basically the product of the product can be denoted by pi. Okay, and the sum can be denoted by either sigma. Okay, so you can just simply say like this. Okay, so in this way, okay, so you can just find the sigma or your total frequency of all the prime numbers. Okay, that's factorial divided by the product of the frequency of every prime number, right? So for example, if you take the previous case, if you take the previous example where x was equal to 12, not x, basically the array was given as so if x was given like 2 3 2, then you see that if you simply say that prime number and frequency. Okay, so for 2 is occurring for 2 times. Okay, for 3 is occurring for 1 time. Okay, so the total number of paths will be equal to the sum of all the frequencies, which is 2 plus 1 factorial divided with the product of individual frequencies. So this comes out to be 3 factorial by 2 factorial. 3 factorial is 6, 2 factorial is 2, so it comes out to be 3, which was the answer also, right? Okay, now for calculating the prime factor and its frequency in a given number, we can use something called as sieve. So for solving this problem, you must be knowing sieve. So sieve is a prerequisite for this problem. By using sieve, you can just pre-calculate the lowest prime factor of every number. Okay, so you calculate the, by using sieve, calculate the lowest prime factor of every number, and after calculating the LPF or lowest prime factor of every number, you can simply find that given a number, any number, let's say n, you can find all the prime factors of it and how many times that prime factor occurs in n, in basically order of log n time. Okay, so you can just easily find it. Basically what you do is that you just keep on dividing the number n by its lowest prime factor each time, incrementing its frequency. Okay, and once you are done, you move to its next lowest prime factor. Okay, so you do something like, so the pseudo code for calculating a prime number and its frequency is like while your n is greater than 1, okay, so you store in some variable, let's say x. Okay, so LPF is the lowest prime factor of any number, which we will just pre-calculate for every possible n till our range. So LPF of n. Okay, now you also have some, you will also have some variable like count will initially be equal to 0. Now what we will do, while your n will be divisible by this x, which is the lowest prime factor, so while it is equal to 0, you will simply divide n by x and you will increment your count. Okay, so in this way, and after doing this, what you will do, you will simply just add this count to your map. So mapping of x plus is equal to this count. So you will declare map somewhere else, or you can just use a hash map as well. So you will declare map outside this while loop, and you will just calculate the total frequency of the prime number x over all the numbers. Okay, so in this way you can just calculate every prime number p and how many times does it occur, okay, in a number a of I, and just sum it up over all the values of ai. Okay, so now if you look at the formula for finding the total number of paths we derived was equal to the sum over total frequency of all prime numbers. Okay, so that's factorial divided by the frequency of every prime numbers factorial. Okay, and we product it over all the prime numbers. Okay, so what we can do, we can just find the total frequency of all the prime numbers, okay, and just take its factorial. Okay, and similarly for every prime number we find it total frequency, take its factorial, okay, and just keep on dividing it with this thing, okay, for every prime number. Okay, so if a prime number, let's say, so what we need to do is, like, if there are, let's say, 3 prime numbers, p1 occurs for x1 times, p2 for x2, and p3 for x3 times. So we need to calculate this thing, x1 plus x2 plus x3 factorial divided by x1 factorial to x2 factorial into x3 factorial. Okay, so what we can do, we can just pre-calculate this thing. Okay, so we initially will be having maybe a vector or array which will just store the value of factorial of any number, let's say n, for several values of n. Basically we can just find what can be the maximum value of this thing, like the sum over the total frequency of all the numbers in the array. and we will also just store the inverse factorials of all these things, because this can essentially be written like this. Since we don't need to find this exact thing, we need to find it modulo 10 to the power 9 plus 7, right? So we can write it also like this, that x1 plus x2 plus x3. Okay, so you find its factorial with 10 to the power 9 plus 7. Okay, and then you multiply with like something like this. Okay, inverse of x1 factorial, then take in mod. Let's call this 10 to the power 9 plus 7 to be mod, then multiply it with the inverse of x2 factorial, mod, and similarly you can just keep on finding. So what we can do, we can just store the values of these factorials and inverse factorial for various values. Now what can be the maximum value that we need to store up to? So if you see that there are n values, right, n values, which x is equal to the product of, for example, in the question given, n is around 10 to the power 5, and each element of our array A can be equal to 10 to the power 6. Okay, so what can be the maximum value of x1? X1 is basically the frequency of p1. So how many times a prime number, what is the maximum number of times a prime number can occur in a given AI or any given number which is up to 10 to the power 6? So that will be nothing but log of 10 to the power 6. Okay, this comes out to be around 20, you can say, even lesser than that. And if there are, let's say, n numbers, so this sum will be equal to 20 into 10 to the power 5, which is 2 into 10 to the power 6. So this thing, like the sum of the total frequency of all the prime numbers will always be lesser than or equal to 2 into 10 to the power 6. So what we will do, we will just store the frequency, we will just store the factorial of all the numbers up to 2 into 10 to the power 6, right? And at the same time we will also store their inverse factorials. Okay, so by inverse factorial, what I mean is that, so in the inverse factorial of some number n, okay, what we will store is basically 1 by n factorial modulo mod. Okay, where mod is equal to 10 to the power 9 plus 7. Okay, now how we can calculate it? We will just the first thing which we will do is like we will say that we will have two arrays, factorial and inverse factorial. So factorial of 1 will be equal to 1, and factorial of 0 will also be equal to 1. Similarly, the inverse factorial of 1 will be equal to 1, and the inverse factorial of 0 will also be 1. Okay, now you will just iterate for I is equal to 2 till the maximum value, which we found to be 2 into 10 to the power 6, right? This. Okay, and you say that the factorial of I will be equal to I into factorial of I minus 1 by the basic property of factorial modulo mod, let's say, and inverse factorial of I will be equal to inverse of factorial of I, right? So this is a function inverse which will find the inverse of this factorial I, right? So you know that it's very easy to implement inverse. Okay, so basically, since we are finding modulo 10 to the power 9 plus 7, which is a prime number, so in that case, like the inverse of some number x with respect to some modulo, let's say mod, if mod is a prime number, is basically nothing but equal to x to the power mod minus 2 modulo mod. Okay, so basically it will be capital or doesn't matter. Okay, so this comes from Fermat's little theorem, but we don't need to care about that. So we can just find it. Okay, you can find it through binary exponentiation in order of log of x time. Okay, so this is the way by which we can calculate the inverse factorial and factorial. Now coming to the lowest prime factor part. So for calculating the lowest prime factor of every number, if we declare, if we have an array of, let's say, LPF, if we say that this is an array like LP of fx will store the lowest prime factor of x, okay, so we know that LPF of 1 will be equal to 1. Now what we can do, we can just iterate from I is equal to 2, I will be lesser than or equal to 2 into 10 to the power 6, I plus plus. Okay, so for in j is equal to I, okay, j will be lesser than or equal to 2 into 10 to the power 6, j plus equal to I, we will simply say that the lowest prime factor of j will be equal to I. Okay, so in this way we can calculate the lowest prime factor of it. Okay, now how it works is like if you are, let's say, 2, 3, 4, 5, 6, 7, 8, 9, something like this. Okay, so obviously the lowest prime factor of 2 will be equal to 2. Now anything which is a multiple of 2, okay, will also be having the lowest prime factor same as 2. Okay, like 4, 6, 8, all of these will be having 2 as the lowest prime factor. Similarly, when you go to 3, now for 3 you see that lowest prime factor of 3 will be 3. Then you go to 6. Okay, so now you don't need to update 6. Okay, so once you did this, you don't need to update it for further. Okay, so before doing this or before running this loop, what you can do, you can just check that if LPF of I is equal to 0. Okay, so initially you just initialize the LPF array with all zeros. Now if LPF of I is equal to 0, which means if some elements LPF has not been found till now, then only you update. For example, when we updated the LPF of 4, 6, 2, 4, 6 and 8. Now when we are trying to update the LPF of 3, okay, so we updated for 3. Now when we go to 6, okay, 3, like j plus is equal to I, so j was initially pointing to 3, now it's pointing to 6. So 6 LPF has already been found, so LPF of 6 is equal to 2, which is not equal to 0, so we don't update here. Then we go to 6 plus 3, which will be equal to 9, and so we update the LPF of 9 to be equal to 3, and similarly we can just keep on doing. So in this way we can find the LPF of all the numbers, and after finding the LPF of all the numbers, it's just that we need to okay, after finding the LPF of all the numbers, we just need to find like how many times all the prime numbers will appear. We can find it using this. Okay, this map of x will store how many times a prime number x will occur, okay, and its frequency. And after finding this, what we will do is like we will just iterate through all the prime numbers, okay, which has been mapped. So what we do is like for every prime number, so for every prime number which will be mapped, okay, so we know that map stores in the form of key and value. So the key will be equal to the prime number and the value will be equal to its count. Okay, so what we will do, we will first calculate the numerator. So the numerator, let's say that numerator is initially equal to 1. So we know that the numerator had like the sum over all the frequencies, like, so we also, let's have a variable like total. Okay, so we will simply add to total prime dot second, because the second element will be equal to the value. Okay, so we find it all the frequency, and after that, after doing this, what we will do, we will simply say that the numerator will be equal to the factorial of this total. Okay, so the factorial of this total, right? And after doing this, what we can do, we need to iterate over the not over the total prime factors, but how many times a particular prime factor has occurred in total. So we again iterate through our array, through our map. So for auto, every element which is present in map, for it each, so what we do, we just simply say that whatever where our numerator, so now numerator will be equal to numerator into inverse factorial of what, each dot second. So each dot second will be storing how many times that particular prime number has occurred in totality. So we take the 1 by the factorial of that number and simply multiply it with our numerator. Okay, and at the end we just simply return our numerator. And when we multiply these together, we also take it modulo 10 to the power 9 plus 7. Okay, so this is the thing which we will do, right? Okay, so this is the way we can just drive our solution. I hope it's clear to you. Now coming to the time complexity, so the time complexity of this will be equal to, okay, so the time complexity of this approach will be equal to order of maxn plus maxn into log of mod plus maxn into log of maxn plus n into log of a of max. Okay, so what is maxn? Maxn is here, is basically 2 into 10 to the power 6. Okay, and this was actually equal to maximum value of x1 plus x2. Okay, so these x1 x2 are the frequency of a prime number p in all the n numbers. Okay, so what can be the maximum value of the total frequency of any prime number? Okay, and if we just sum it over all those prime numbers, what is the maximum of that? Okay, so that we call it as maxn. Okay, so as we are just calculating the factorial of all those maxn numbers, okay, so calculating the factorial of all those maxn numbers will require order of maxn time. Now calculating the inverse factorial of all those maxn number will require maxn into log of mod time. Why? Because like there are maxn numbers for which you need to calculate the inverse factorial, and inverse factorial you are calculating by using an inverse function, and inverse function is basically doing binary exponentiation. So basically, in order to calculate the inverse of some number a, okay, so this will be equal to a of mod minus 2 modulo mod. Okay, so this comes from Fermat's little theorem. So since binary exponentiation works in order of log of the exponent, so here exponent is mod of mod minus 2, so calculating the inverse of some number works in order of log of mod. So calculating it for maxn number will require maxn into log of mod time plus maxn into log of maxn. This is for calculating the LPF of all the numbers, lowest prime factor of all the numbers, right? Since there are like 2 into 10 to the power 6 numbers, so it will require maxn into log of that number. And then we are just going through all the numbers and just prime factorizing it. So a number can have at most log of a of max number of times a prime number p can occur in that number. Okay, and if you just factorize all the n numbers, that will require n into log of a of max, right? So this will be the space time complexity for this, and the space complexity for this will be equal to order of max of n. Why? Because here we are just using two arrays, or you can say vector, for storing the factorial and inverse factorial, and also the lowest prime factor of all the numbers up to max n. So that's why the space complexity for this will be equal to order of max n. Okay, so I hope it's clear to you. So if you enjoyed the video, please like, share and subscribe our channel. Thank you.